Good morning, ladies and gentlemen. May I have your attention, please? Thank you. I appreciate you having your reading questions out and ready to go. It makes it a lot quicker as I come around the room and see if you're credit eligible for that 5th point Infinite Campus. At this time, I ask everybody stop and go ahead and take a look. Make sure you got a red mark for today, the 10th of September. Raise your hand if you did not get a red mark. Everybody good? Great. So we've got lots to do today and a shortened amount of time to do it. We're working with our club org schedule today, our club org schedule. And so today you can see that our early 3A class goes from 11:52 to 1:16. Okay, and so we want to make sure that we get our important discussion completed by 1:16 today. So we've got lots to do, including our practice quiz check. What we're going to do now is take a look at our bell work and describe in our own words what it means to be a mathematical function. So last class we talked about some different pairings, right? A relation is just a collection of pairings, a collection of ordered pairs, a collection of points. A function, right, is that special kind of pairing in which each input is paired with a unique output. If a given input occurs, right, more than one time, it has to be paired with the same output each time. Otherwise, it's not a function. So in our own words, what a mathematical function means is each input is paired with a unique output. That is one and only one, right, output. So if 2 is paired with 7 in one point, and 2 is paired with 8 in another point, it's no longer a function. However, if I scan my list of pairings and no inputs repeat, then it's guaranteed to be a function, right? It's guaranteed to be a function if no inputs repeat. I don't care what the outputs are. They could all be the same output. It could be 2, 7, 3, 7, -8, 7. That's still a function because no inputs repeat, and I don't care if the outputs repeat. I'm concerned about the inputs repeating when I talk about a mathematical function. We'll also look at that again in our table, and you saw that in several of your homework exercises. Number 2, we can evaluate. If I'm given a function rule, I can use differing notations to evaluate for a given input value. So in the function f, which accepts input values of x, can I replace all of my x value inputs with -3? Certainly. In fact, I'll simply rewrite my function definition. My function rule is 2 times input squared plus 5 times input minus 7. And evaluate, except everywhere I see an x, I'm not going to put x. What am I going to put? Bruce? -3. Thank you. So I'll put -3 everywhere my function f accepts inputs of x. Now we'll go ahead and follow our order of operations. You want to make sure that you're watching your signs, positive versus negative. Remember, there's a battle going on right here, right now. This 2 is trying to multiply the -3. This 2 is trying to square the -3. In our battle between multiplication and exponents, right? Who wins every time? Lucas? Exponents, right? Exponents. Thank you. So we'll go ahead and do the -3 squared first before I ever do the 2 times that multiplication out front. So 2 times 9 minus 15 minus 7, which is why I get 18 minus 15 minus 7, and so I'm getting 18 minus 15 is 3 minus 7 is -4. Goodness. Raise your hand if you already had -4. Did anybody else get -4 before I did? Yes. Way to go, you guys. Great. Thanks, hands down. We can do the same thing whether our function was given in mapping notation or in function notation. It's the same information, just different packaging. Right? It's the same cereal in a different box. I can still evaluate my function, g, which accepts inputs of x and maps them onto outputs in accordance with the rule of 5 divided by the output and then plus 8. It's just that I'll replace my input x with -1. So I'll rewrite that. Except in this case, every time I see the input, I'll put -1 and work it out. Watch your sign. Positive divided by negative is negative. So I get -5 plus 8, and then I combine my terms, and I get 3. Raise your hand if you already had 3. You already had 3? Yes. Good job, you guys. Great work. Thank you. Hands down. Let's take a look at our table. functions can be written not only as a rule, a function equation, a function machine, and it can also be represented in a table. In this particular table, we're told that h is a function of t, but asked why. So as I look at this table, why is h a function of t? Go ahead and quietly tell your partner. Why is h a function of t? And you can think about number one. Okay, enough talk. Now we eat. So why is h a function of t? And what did you guys come up with, Olivia and Jimmy?
We said that t has no same values, and it's the x in the situation, and h is the y.
Absolutely. So because t does not repeat, there's no repeat t values, this is guaranteed to be a function. Even if all the outputs were the same, it would still be a function because my independent variable values, my inputs, don't repeat. That guarantees that each input is paired with a unique output. There's no way for 4 to be paired with more than one output if 4 only occurs once as an input. You guys see that? It doesn't matter what the outputs are or how many times they repeat. I'm concerned about the inputs repeating. Good job. So why is h a function of t? The short reason is no input t values repeat. Right? Guaranteeing, that sure looks like a Q, not a G. Guaranteeing that each input is paired with a unique output. That was close. And lastly, find h of 10. Go to the function whose name is h and see what function value, what output, what y value is paired with the input 10. So as I look at this evaluation, h of 10, I remember inside the parentheses goes the input. So the input is inside the parentheses. That means that 10 is an x value or a y value. Well, in this case, neither. But in a point, it would be the x value because it's the input, right? Independent variable input, x value. In this table, it's not the x value. It's which value? Bless you. The 10 is a t value or an h value. Sydney? A t value. So I'm scanning the problem and I'm trying to find when t equals 10, right? When t equals 10, the corresponding function value or h value or output value is 45. So h of 10 equals 45. What point would be represented by that function notation? H of 10 equals 45. The point input, comma, output. 10, comma, 45. The input 10 is paired with the output 45. And so there's 3 different ways to write it. A table, function notation, h of 10 equals 45, and a pairing as a point, 10, comma, 45. They all mean the same thing. When the independent variable is 10, the dependent variable value is 45. All right, what questions do you guys have about our Bell discussion today? Did I spell guaranteeing correctly? We don't want any quarantine, right? We want guaranteeing, okay. Guaranteeing, I think we're good. That's a GU. All right, ladies and gentlemen, let's switch gears. I want to make sure you have your solutions now, your solutions to your practice quiz. And so once again, the practice quiz will not be passed in. It's not going to be turned in right now, but I want you to get the right answer. So very quickly, we're going to make sure that you have the correct solutions to it, so that you can make corrections.
Yeah, I got it. Thank you.
Brendan, anytime you're trying to get the stuff from the side counter.
Okay.
Yes, and I have the link to the recording online, so you can
Okay.
recording with the PDF.
Thank you.
You're welcome. Okay, guys, we ran out of time during 1A, so I want to make sure that we're moving a little bit quicker today, which means our homework time will be our homework check will be a little scrunched, as will our quiz corrections. Again, this does not count for a grade, but I want you to have the correct answers so that in the next 2 days, right, you can go and make sure that you're able to solve these equations, correctly going into our day 7 quiz, which counts for a grade. I'm sorry, Bruce, did you find that? And did you need your day 3 notes? Or do you already have the day 3 notes? Okay, cool, thank you. So, in the first one, multiplying everything by the least common denominator is our means for clearing the fraction. When we do that, you can think about multiplying each term by 12/1. That will reduce your fractions. We get a final answer of x is negative 16/5. When I'm doing a squaring, we must consider both the positive and negative square root. That's why we get 2 solutions, right? When we undo a squaring equation, in this case, b is positive root 12 or b is negative root 12. If you remember how to reduce your radicals from geometry, that's awesome. For now, you'd still get full credit for this top line at this stage, so long as you had both the positive and negative square root of 12. 2 separate solutions. In our third one, clearing the fraction would be the same as multiplying every term by 9. Inverse operations would then yield r equals negative 3/8. Take a minute and make sure you have the correct solution for that. You can write it down in pen and add it to yours and use this as a resource to study. Getting rid of absolute value bars is the same as breaking it up, right? Break it up. I'll go ahead and add or subtract, multiply or divide to get the bars alone, and then I'll break it up into 2 separate equations. One where the quantity inside the bars is set equal to the positive distance number. One where the quantity inside the bars is set equal to the negative distance number. How come? Because there's 2 numbers that are a given distance away from 0 on the number line. In this case, the 2 numbers that are a distance of 3 away from 0 on the number line are positive 3 and negative 3. That's how I break it up. And then I can continue on solving as normal. Q is 1 or negative 1. In number 5, solving for C gives me the positive and negative square root of E over M. I must consider both the positive and negative square root when undoing a squaring. And so if you're creating the radical as a means for undoing a squaring, that's when you get the 2 solutions. You must include both the positive and negative square root. Ethan?
If 6?
Yep.
Would it be a fraction of side fraction or no?
So let me guess. Did you divide by n first or r first?
Yeah.
Did you divide by r second then?
Mm-hmm.
So you got mega fraction, right? Ethan, this is mega fraction, this is Ethan. So we got PV over n all over r. This is a fraction within a fraction, which is bad mathematics. But that's okay. I know division is the same as multiplication. I can rewrite this as PV over n divided by r is the same as PV over n times the reciprocal. What's the reciprocal of r? 1 over r. And so I could rewrite T as PV times 1 is PV, n times r is nr. Woo! Lo and behold, there's our answer all along. Does that make sense, Ethan?
Yeah.
So you can get there in 2 steps, but it's really quicker to do it 1 step. Number 7, clearing the fraction by multiplying everything both sides by 2. And then subtracting L is 2c minus k. And number 8, undoing a squaring requires the consideration of both the positive and negative square root. So there's 2 answers in number 8. Everybody get those down? And note, we cannot apply that radical. We cannot apply the square root to a sum or difference. So because this was subtraction here, we cannot reduce that. That is not equivalent to c minus b, or positive or negative c minus b. If this were multiplication, we'll see in Unit 3 that we could simplify the radical through multiplication, but we can't simplify the radical. We can't apply the radical through subtraction or addition. So that's as far as you can go. Everybody have your correct answers? The next 2 days, you want to make sure you're making corrections, so you're ready to go for your quiz on day 7. And now let's take care of our homework checks. So remember, in this class, we do homework checks 2 different ways. First, make sure that your name. Our hour is 3A. And assignment number 3 are clearly labeled on top of your assignment. Give yourself credit in pencil for those of you who completed out of 36, please, out of 36. Out of 36 problems, the number you did in pencil, divide, enter, multiply by 4. And if you showed me your reading questions, 1, 4, 1, 5, you guys have been doing a nice job with that. You're eligible for that fifth point. Round your infinite canvas score to the nearest half point, 0 to 5, and box that nice and big at the top of the page, please, so it's easy for me to see and get you credit for the hard work you're doing outside of class. What questions do you guys have on your infinite canvas score today? Then we're pencils down now. We're going to go ahead and get our accuracy fraction. We'll circle that in pen next to our infinite canvas score. If we did 36, it'll be out of 36. If we only did 16, it'll be out of 16, and so on and so forth. In the interest of time, we're going to have to move a little bit quicker today. So today we'll have to go a little bit quicker to make sure we get to our vertical line test at the end of the discussion. So a function is like our Bellwork number 1. Set of order pairs where no two pairs have the same first coordinate. A function is a type of relation, so all functions are relations, but not all relations are functions. For A is yes. It's a function. Every value of S is associated with only one value of T. B, no. There'd be two different S values generated by T is 25 or T equals 100. 5, yes. It's a function. 6, yes, it's a function. 7, no, not a function. 8, yes, it's a function. 9, D is the dependent variable. B, 120. 11, P is 75. No, it's not a function for 13. 14, A, algebra. B, binomial. C, calculator. 15 through 20, perhaps my favorite, translating, right, verbal descriptions of the math statements. So 15 is B over M dollars. 16 is N minus S dollars per pound. 17 is K times L outfits. 18 is P plus I dollars. 19 is G over M times N eggs. And 20 is H plus MT hits. Courtney. You don't have to for your grading right now, but you should make sure to include them in the future, particularly in our test or quiz when we're talking about functions in context. So in context is in the some real world setting, but you don't have to take them off for your homework right now. Good question. Next section, our 1-3 section, that's read f of x. Right? F of x is how we say that. The function t maps a onto my function rule. 3a is half times x times the quantity 5 minus x. 5, 4.80. 6, 0. Number 9 is 186.8. 10 we did in class. The function t accepts input values of c and maps them onto outputs in accordance with the equation 1.8 times c plus 32. 12 is the dependent variable. 13a is negative 12, b is 18, 14 g of x is given by 12 minus 2x, 15 a is r, b is 288 pi, c is 36 pi r cubed. 16 is 1. 1829.4, B, the change in average price of a gallon of gas between 2005 and 2006. In letter C, it looks like the average price increased by 29.4 cents from 2005 to 2006. Yikes. Number 19, the years 2000, 2003, 2004, 2005, 2006. Number 20 is the year 1999. 21, A is 12, B is negative 212. 22, yes, it's a function. 24, A, $1,207, B, $657 plus 50 N dollars. And 25A, Y is 6, B, Y is negative 4, C, Y equals K, and X equals H. And that should round out our assignment. I know that was rip-roaring and fast. We wanted to make sure we have time for a vertical line test at the end of today's discussion. So we are moving a little bit quicker with our check today. Please do the best that you can in our time provided. Give yourself an accuracy fraction about how well you did. Make sure your name, 3A, and number 3 are clearly labeled at the top right. If you have multiple pages, kindly staple them together by using a stapler from the front activity table or the side activity table. Final check, infinite canvas score box. Pass from the back to the front, please. Front rows, make sure they're facing the same direction. I appreciate your help. You would, but because it was only a third of a point, that's still Thank you. Go ahead and pass from the back to the front row, make sure they're facing the same direction. There's a staple over there too, guys, on that side. Where'd it go? Yeah.
Can I go to the
Okay,
restroom?
hurry. Good, that goes in the back of your, that's back there.
Yeah. Well, like
Your house, right?
Yeah.
So you still get full credit on it?
Yeah.
So, did
But I
I
didn't
pass?
do that.
So,
Good. Or
I
try
would,
to finish it.
yeah, I would finish it, and I did post the solutions if I wanted to, so you can check it out, and I'll be wondering back here. You guys. That's great. Pretty good with number 3, if you did it, number 3. Thank you, ladies and gentlemen, for your help grading your assignment each and every day. I appreciate that. Today we're going to determine the domain and range of a function, and we're going to be working in context so we can connect those independent versus dependent variable values in the context of a real-world problem situation. So we want to be thinking in terms of units and what our function represents. We're also going to determine whether or not a given relation is or is not a function. We kind of saw that in our bell work a little bit. But we're going to use our graphing calculators to make tables and graphs with our graphers, so that's pretty sweet. Let's go ahead and get going then. So we know that the domain of a function is a collection of all the independent variable values, all the inputs, right? All the x values. The collection thereof is the domain of a function. We know that the range of a given function is the collection of all the dependent variable values, all the outputs, all the y values. Set builder notation is a way that your textbooks offers to write a range of values, right? A range of values that are acceptable. In this case, our example says the set of all x values such that x is in between 0 and 70. You could use a mod symbol, that vertical slash, that vertical line, or you could use a colon. I prefer to use the colon, but it's personal preference. The cursive brackets are informing the reader that you're going to be talking about a set of values. The inequality symbols mean that we're talking about a range of solution values, an infinite number of solution values. And this could be one-sided inequality symbol, or it could be bounded here, two-sided inequality symbol, depending upon what range you're trying to describe to the reader. Our real numbers can be divided into many subsets, and this is a great opportunity for Mr. Fritz's caveman story, right? It's not quite as good as the Croods, but almost, right? Classic movie. So the caveman wakes up in the morning, and he stretches, and he goes outside, right, to count his sheep in his pen, and he counts his sheep, 1, 2, 3, 4, and so on, and the natural numbers are born, or the counting numbers. So the natural numbers, or the counting numbers, refer to those numbers 1, 2, 3, 4, those numbers that you could count on your fingers and your toes forever and ever. Well, the next morning, our caveman wakes up, stretches, goes outside to count his sheep, and lo and behold, overnight, the wolf had come and gobbled up all his sheep. And so we're introduced to another important number, 0. 0 sheep remaining. So the collection of all natural numbers with the important addition of 0 is called the set of whole numbers. So the whole numbers are 0, 1, 2, 3, 4, and ever on. So our caveman, who had lost all his sheep, went down to the bank, right, and took out a loan and was promptly introduced to the negative numbers now as well. And so we've got negative counting numbers, 0, and the positive natural numbers together are referred to as the integers. all real numbers can be expressed as a decimal, either terminating or non-ending, decimals that go on forever and ever and ever. Rational numbers are those real numbers that as a decimal either stop or fall into a repeating pattern. They can always be expressed as a quotient of two integers, a fraction. So a rational number can be expressed as a quotient of two integers. And it's a rational number. I can write it as a fraction with integer numerator and integer denominator. As a decimal, rational numbers either terminate, that is stop, or they fall into a repeating pattern. .25 is a rational number because it stops when I write it as a decimal. I could also write that as a fraction, 6 1/4, right? 6 1/4 or 25/4. 6.25 is a rational number. The number 1.333333 forever is also a rational number. While it as a decimal goes on forever and ever, it's still rational because I could write that as a decimal. I'm sorry, as a fraction. It would be 4/3. If my decimal goes on forever and ever, but does so in a repeating pattern, as this one repeats, it's a rational number, and I could write it as a fraction. Irrational numbers, when written as a decimal, go on forever and ever and ever, but don't stop. They don't fall into a repeating pattern. Irrational numbers are typically numbers that are non-perfect squares inside of a square root, or are transcendental super numbers, like the most famous irrational number is likely pi. Euler's number, which shows up in a variety of real-world applications involving growth and decay. E is another super irrational number. What about the square root of 25? Well, the square root of 25 would be rational because that radical does contain a perfect square. It would reduce to an integer, so that's still rational. But the square root of 24 is irrational. If there's a non-perfect square inside of a square root, that's going to be irrational as well. As a decimal, they go on forever and ever without stopping and without falling into a repeating pattern. Let's go ahead and figure out which sets these numbers belong to. So consider negative 16.3. Which of those subsets, if any, does negative 16.3 belong to? Well, because it can be written as a decimal, it's real. And so negative 16.3 is real. Because as a decimal it terminates, that is, it stops after the 3, it must be rational. If I can write a number as a decimal that stops, it is guaranteed to be rational. However, it's not an integer because it has a number after the decimal point. So it's not an integer, which means it's not going to be a whole number or a natural number because it's negative. Negative 163, it's a real number. It's rational because it stops. And it's also an integer because it's a negative whole number. It's not a whole number because it was negative, so it can't be a natural number either. The square root of 8, as a decimal, goes on and on forever without stopping or falling to a repeating pattern. So while it's real, it is also irrational. It's irrational. I cannot express that as a fraction, as a quotient of two integers, so it's irrational as decimal, goes on forever and ever. That's like a non-perfect square inside of a square root is going to guarantee to be irrational, versus the square root of 9. Because that square root contains a perfect square, it is rational. In fact, it would reduce to an integer. Because it's positive, that integer would also be a whole number, and it's a natural number because I can count it on my fingers or toes. In this case, I only need fingers because it's just 3, right? That's fun. So root 9 was all those things. What about 107? Go ahead and write down the sets that 107 belongs to. be ready to share with the whole class. I think it's on the next one now. Next page, I think, is 107. So which sets, if any, does 107 belong to? So what are you getting for that? Ethan?
Real, rational, integer, whole number, rational.
Wow. Boy, howdy. So all of those sets, right? All of those sets, 107 belongs to. Raise your hand if you have the same. You have all those. Absolutely. Good. Thanks. Hands down. 41/28. That's real. It's rational because it's expressed as a fraction, a quotient of integers. 41 is an integer, over 28 is an integer. That's by definition a rational number. As a decimal, I know that that would either stop or fall into a repeating pattern. Turns in with sevenths that are hiding in the denominator would actually go on forever and ever and ever without stopping, but it would do so in a repeating pattern. So this is real, rational. Because there's places after the decimal, it's not going to be an integer, so it can't be a whole number or a natural number. Pi is a real number and perhaps the most famous irrational number. If a number is irrational, then it can't be rational at the same time. As a decimal, pi goes on forever and ever without ever stopping or falling into a repeating pattern, so it's irrational. 56/28 is real. It's rational because it's a fraction, a quotient of two integers. Look at it. It's a fraction, a quotient of two integers. However, if I were to reduce it, it'd also become an integer, a whole number, and a natural number. Boy, howdy. Because isn't that just 2? 56/28 is just 2. So that's all those things again. And lastly, the square root of negative 49. Which of those sets does the square root of 49 fit in? Ben?
None.
None of them. No way, no how. I can't take the square root of a negative number because no number squared is going to give me a negative result. No real number, I should say. No real number squared will give me a negative. Wait a minute. What about negative 7? Will negative 7 work? No, because negative 7 times itself would be negative 7 times negative 7 is a positive 49. So no, this is a non-real. This is an imaginary number. This is an imaginary number. In fact, imaginary numbers have a lot of use in mathematics. In fact, imaginary numbers show up anytime you're dealing with electrical circuitry and currents or fluid flow and aerodynamics. And so actually non-real numbers are used in real mathematics, but we won't do that until semester 2. All right, does a number exist that belongs to all the categories above? We're not talking about square root of negative 49, we're talking about just these categories, all right? What do you think, Jenya?
No,
No, how come?
because it can't be rational.
Good, and so we've got the irrational versus rational component. A number cannot be rational and irrational at the same time. All real numbers are either rational or irrational. A number doesn't exist that can be both. Good job. So no way, Jose. How's that for emphasis? All right, let's go ahead and take a look at some domain and range questions. So I'll go ahead and do my domain in green. If I'm given a tabular representation of a pairing, I know all my inputs, all my top row are my x values, my inputs, my domain values. If it's a discrete number of entries, in this case there's only 5 values, I'll simply write that as a list of numbers or values separated by commas. I like to use cursive brackets to let the reader know I'm talking about a set of values. So we'll go ahead and open up my set with the left cursive bracket, and I like to list my input values in increasing order because it's good math manners. You could list 8, 12, negative 7, 0, 6, but I'm going to list negative 7, 0, 6, 8, 12, because I like to follow good math manners. B, the collection of all outputs, because it's a set. I'm going to let the reader know by using cursive brackets. I'm going to list my values in increasing order because I like to use good math manners. And because negative 5 appears more than once, right? I don't need to list it more than once. I'm already telling the reader that negative 5 is an output. If it occurred every time, I only have one number in my range, negative 5. That's why I don't have to list it more than once, even though it occurs more than once. Next, 0, 3, 22. And lastly, g of 0, 0 is inside the parentheses. 0 is my input value. 0 then must be my top row value 0. Not this 0. 0 must be referring to this 0 because it's an input value inside the parentheses. So what function value, what g value is produced when I input 0 into my function? Looks like -5. So g of 0 equals -5. That's referring to the point 0, -5. However, the answer to g of 0 is -5. We can also look at a graphical representation of a function. In this case, do I have a discrete list of values, like 5 values for my domain? Well, no. I've got an infinite number of values because there's an infinite number of points connected to make that graph. I could sit here and list x values till I was blue in the face, right? And still not list all the x values for which a picture is produced. Therefore, I can't just do a list of numbers with commas. That's the utility of that set builder notation that we saw in our notes earlier. So now we'll go ahead and write my domain still in green. It will be the set of all x values such that my least most x value, my left side of my x window would be -1, -2, -3. It looks like -3 is my leftmost x value for which a picture is produced, less than or equal to x's in my picture, less than or equal to my greatest most x value, the right side of my window, the rightmost x value for which a picture is produced is 5. And so set builder notation is a convenient, streamlined way to write a set, a collection of values, an infinite number of values, all of which are in between -3 and 5. My range, again, I'll do in blue. This is the set of all y values, all output values, all y coordinates. And this time, my least most y value produced is all the way at the bottom of my picture. So what's the lowest y value that's ever produced? -3 is my lowest y value down here, right? -3 is my lowest y value down here, up until the greatest y value produced, the topmost y value produced is y equals, I'm counting on my axis, 1 to 6. So we're looking from bottom to top when we talk about range in y, the y coordinates in blue, we're looking at bottom to top. Versus when we're looking at domain, we're looking left to right. What's my x window for domain in green versus my y window in blue? You guys see? K of 3 asks for what function value, what k value, what output, what y coordinate is produced when my input, x value is 3. Those are saying go to my graph, hop on the graph of your math man, your math woman, and you're moving along it until you get to an input, an x value of 3. Where does that happen? No. Yes, right here. The x value 3 is paired with what output value, what y coordinate? Looks like -1. So the point that refers to, would be 3, -1, right? That's 3, -1. However, k of 3 equals -1. So the answer is just the -1. But I got that by looking at the point 3, -1. And lastly, we could consider a function f given symbolically, that is a function equation, f of x equals 1 over 9x. Sometimes it's easiest to think about domain in terms of what values cannot x equal. As I look at f of x is 1 over 9x, I know that I cannot divide, right, by 0. And so if there were an x value that produced a 0 on the bottom of a fraction, I know that that would not be in my domain, my set of allowable input values, my set of allowable x's. And so what will we do? Well, it's easiest to say that x can be anything except for 0. So how would I write that in set builder notation? Easy cheesy, I'll say the set of all x's such that x doesn't equal 0 is the quickest, most efficient way to write that. So x can be anything except for 0. How come? Because I can't divide by 0. I can't have a 0 on the bottom of the fraction. So if I can find an x value that would create a 0 on the bottom of the fraction, I have to cull that from my domain. I have to take it out of my domain. In order to get the range, we're going to have to look at our grapher. So that's a little bit trickier. Everybody, let's go ahead and do our graphers now. What I asked that you do at this time is get your graphing calculator out, and we're going to go ahead and do some graphing.
There's a calculator.
Yeah, just sign one out, please, and put your name in the calculator. So we've got our graphing calculator, and we're going to go ahead and practice inputting a function into our calculator. To make this work, right, we need to make sure that we're paying attention, we're following along, and we're checking with your partners. So you guys are going to help each other out to make sure that we're producing the appropriate picture and table on your graphers. To do that, right, we're going to go ahead and utilize the emulator up here, and we're going to follow along carefully. So here we go. In order to enter a function into my graphing calculator, I go to the y equals menu. Everybody go to your y equals menu and make sure that anything that's in there is cleared out by pressing that clear button underneath the arrow pad. You also want to make sure at the same time that your plots are turned off. And so some of you are going to have your plots on top highlighted, one or all of them. In order to graph our regular functions, we need to turn those off. And so everybody take a minute and make sure that your plots are unhighlighted. So up arrow to any plots that were turned on, that were shaded in, you're going to press enter to toggle them off. You want to make sure that none of your plots are on. None of your plots are highlighted. Everybody good? Great. Nothing's entered yet in my function menu. I'm going to take this opportunity to return to my standard window. So I'm going to press zoom. That top toolbar, the middle button is zoom 6 for standard viewing window. So I'm going to do zoom 6 and it'll automatically return to your regular graph. Zoom 6. Does everybody have your regular axes here? Regular axes? No picture, just regular axes. Everybody good? Hooray! Now let's enter our function rule into our y equals menu. So our top toolbar, first button is y equals. We're going to enter 1 divided by 9x. Uh-oh. That 9x is all in the bottom of a fraction. If I don't use parentheses, my calculator is only going to divide 1 by 9 and then put the x back on top. That would be graphing 1/9 x, which would just be a line. Turns out that this is not just a line, and to show my calculator that I mean to divide 1 by the entire term 9x, I need to put parentheses there on my own. Everybody add parentheses around your 9x. So 1 divided by left paren 9, x is the variable button right here, second row, second column, close parentheses with the right parenthesis, and there's my 1/9x. Okay, good? Now we're going to go ahead and press the graph button. Top toolbar, right side is graph, and we're going to see what this picture looks like. It looks like my standard viewing window doesn't do a very good job of showing this behavior. So what I'm going to do is get a better picture by zooming in. If I could zoom in, I might get a better picture because it looks like something's going on. Quite frankly, it looks sort of boring over here on the ends of the graph, but in the middle, it looks like something's going on. So we're going to zoom. Again, that's top toolbar, middle button, zoom. 2 for zoom in, enter. So I'm going to zoom 2, enter. And when I press enter from the graph, it'll zoom into a smaller window. You guys seeing that? Now I can see a little bit more. So zoom 2, enter, press enter again. Zoom 2, enter. And we should be producing this picture. And it looks to me like my function values, as I get closer and closer to x equals 0 from the left, are shooting off towards negative infinity. My function values are shooting off the charts towards positive infinity as x gets closer and closer to x equals 0, but from the right hand side. Let's go ahead and trace on my function. So what I'm going to do is I'm going to press trace. And when I press trace, I notice what y value is paired with x equals 0. What? Nothing. Nothing is produced when x equals 0. Is that a shocker? No. I know that x equals 0 was not in my domain of the function because it created a bottom on the, a 0 on the bottom of a fraction, which is not permissible. I can't divide by 0. And so I expected a picture not to be produced when x equals 0, and we're finding that in our actual graph. When x equals 0, the function shoots off the chart, it doesn't exist, right? As I get closer to it, on one side we shoot towards negative infinity. As x gets closer to 0 from the right, my function value shoot up to positive infinity. Okay. The range then is the collection of all outputs. And so my outputs that are produced look like all the y values are produced because my function shoots down towards negative infinity and up towards positive infinity. It looks like all positive numbers and all negative numbers will be produced as my function shoots off the charts. Except right here, it looks like my function's leveling off as my y values get closer and closer to y equals 0. And so if I consider my original function definition, the only way for a fraction to equal 0 is if which part is 0, the top or the bottom? The top. The only way to get a fraction equals 0 is if the numerator is equal to 0. What's the numerator on this function? 1. Will it ever equal 0? No, it's fixed at a constant 1. So there's no way to make this value of the overall fraction equal to 0 regardless of what we choose for x. Therefore, all y values are produced except y equals 0. Again, I'll write that with set builder notation as before. I can write that as the set of all y's such that y doesn't equal 0. And lastly, I can do f of negative 3 by evaluating my function, or I can do it by a trace. And so let's go ahead and first evaluate. Everybody, just like our bell work, go to the function whose name is f, which accepts input values that are x's, except everywhere you see an x, don't put x, put negative 1/3. So I get f of negative 1/3 equals 1 over 9 times negative 1/3 equals 1 over 1/3 of 9 is 3. So 1/3 of 9 times a negative is negative 3. So I get f of negative 1/3 equals negative 1/3. Let's check with our emulator, with our calculator. On my calculator, I could evaluate if I'm looking at a graph by using the trace button again. So we'll do trace, and then enter your x value of concern. Our x value was negative 1/3. So do negative 1 divided by 3, and tell the calculator you want it to trace when x equals negative 1/3. So everybody trace negative 1/3, enter. When you press enter, the cursor, voila, should jump on the graph at the coordinate when x is negative 1/3 and pair it with what output? Well, it's pairing it with the output negative 0.33333333. What y value do you suppose is negative 0.33333333? Negative 1/3. So we've done it algebraically, and we've done it with our calculator. So how do we do that? Trace, enter the x value of concern, enter, and it'll jump the cursor onto the graph and pair it with the corresponding y value. That's pretty sweet. You guys good with your calculator so far? We're going to do one more activity with the table a little bit later. Let's go ahead and continue our discussion then. We've got lots to do. I'm going to go ahead and call people down to the board now. If you're called down, I want you to go ahead and use your fingernail to drag the tab into the appropriate vortex. And so if it was my turn here, I know that my x values, right, make up a function's domain. So if I was called to the board, I'm going to go ahead and take my fingernail, and I'm going to take my x's, and I would drag them into domain. But let's say that I got nervous and I put them in range, it'll spit it right back out. And so I know that I'm correct if I put it and it gobbles it up versus if it spits it back out. The vortex swallowed x value. So let's go ahead and come on and drag a tab with your fingernail into the appropriate spot. And you can kick the party off, Mason. Let's go ahead and drag one of those tabs with your fingernail into the appropriate vertex. When you get to the board, say which tab you're dragging.
Y.
Thank you, Mason. Nathan, come on down. Mason put the y values in the range and it swallowed it up, so we know he's right. Okay?
I'll do left column.
Left column, let's see. Nathan says left column is domain eaten up. All right, come on down. Maggie, your choice. Open board. Any order.
Right column.
Right column, let's see. Excellent, right column went into range. Nice work, thanks. Ben, come on down.
What are you doing?
Independent.
Thank you. Other Ben. This is fun.
Dependent.
Dependent. Thank you. Cameron.
Which one?
Oh, sorry. Cameron with a K and a Y. Let's see where they go. Awesome. Thanks. Cameron with a C and an O.
I'll do argument.
Argument. Let's watch. Argument. Correct. Argument is just the book's synonym for input. So it goes in the domain. Thank you. Come on down. We've got another crayon. I know we've got another crayon. So. Lucas.
Right. Between output and range.
Output into the range. Awesome. Thanks, Jimmy.
Top row. That's domain.
Top row is domain. Excellent. Thanks, Jenya. By value, we mean function value. We mean function value.
Is that the range?
Let's see. That's the range. Awesome. And Luke. I was going to call you right after Lucas. We'll get Luke and Lucas down and awesome. Thank you, Luke. Nice work. So that was bottom row went into range. Yeah, don't be shy, Isaiah. Yeah, thanks for participating, guys. Thanks. That was awesome. Hopefully we can do some more vortex sorts. Let's go ahead and take a look at our table and our calculator. So again, our calculator, what we're going to do is manually adjust our table set feature. Everybody, let's go to our graphing calculator. And before we enter a new function, it's always good math manners to clear out your stuff. So everybody, let's go to our y equals, clear out your y equals menu, zoom 6 to return it to its standard viewing window, -10 to 10. So zoom 6 and it'll automatically jump to the standard viewing window, -10 to 10. And now let's go ahead and consider that suppose a puddle of water is evaporating and its depth d of t in inches after t days is given by the formula d of t equals 16 minus 16t squared. Everybody, let's enter the equation into our graph. So we're to the y equals menu. That's our top toolbar, y equals. We're going to enter 6 minus 1/16. And for my variable button, t, I'm going to use x. My x, t, theta, n, bless you button is x. It'll show an x, and then squared is the fifth row, first column button is squared. You can also do caret above the division key, raised to the second power is squaring. I like to use the shortcut key though, so that's pretty sweet, highlighted in red. Oh yeah, that's what I'm talking about, Ethan. That's what I'm talking about. So 6 minus 1/16 x squared. Enter in our grapher. I'm going to go ahead and screenshot that. And now we're going to go ahead and follow the prompts. We're going to set up a table to start at x equals -5 and generate y values in increments of 1. Generate x values in increments of 1. And we're going to use our table set to do that. So everyone carefully listen. We're going to go to table set. That is second window. So second window is my top toolbar second button. That'll bring up my table set. In my table set, I want to ask the calculator to start generating values at x equals -5 and goes by a step of 1. So I'm going to go ahead and make sure that my table start is -5. My t step or x step or change in table or delta table, whatever your calculator says, is 1 because I want it to go by ones. Make sure that your independent variable and dependent variable are both set to auto. Everybody good? Yeah. I want to screenshot it. And now let's go to my table. So, I didn't want to do graph. How do I do table? I do second graph. And so I'm going to do second graph. Sorry about that. Second graph. And I should now generate this table. Go ahead and show your partner your calculator and make sure you guys agree. Everybody's able to generate the table? -5? It's pretty bomb, y'all. Okay, guys, let's go ahead and now answer some questions that are asked. The values in the x column represent which variable? So my x column here, my x column, my calculator spit out x even though I was trying to enter t. And so my x column here should represent t, which is measured in, is t measured in inches? What do these things stand for? What's t measured in? Days. And so t days since the problem started. The f of x column, the y column, represents which variable? Well, that's not t, that represents what? What variable? My depth d, so d inches. D inches. Do all of the ordered pairs in this table realistically model the puddle of water situation? Why or why not? What's wrong? I mean, what values don't make sense in this problem if we're talking about the depth d of water in the puddle after t days? What values don't make sense here? Nathan?
The negatives for the input.
Yeah, I agree. And I would also argue negatives for outputs wouldn't make sense for depth of puddle. We could have negative depth, right, if we're diving in the ocean or something, but we wouldn't have negative depth of a puddle that's evaporating, right? So I would say, no, we need positive values for this problem situation. Need positive values for time in days and for depth in inches. Determine the water depth after 6 days. So if I want to determine the water depth after 6 days, does my current table show that? No, but we could certainly get there. All we have to do is scroll with our arrows. So everybody, let's go ahead and scroll with our arrows. I'm going to hold my arrow down, and I'm going to scroll down until I get past 6. Settle down, settle down, settle down. You see that? I went crazy. All right. So as I look at my table, can we answer questions like, what's the depth of the puddle after 6 days? Yeah. The depth of my puddle after 6 days is 3.75 inches. So I can write that in function notation. I would say d of, thank you, Bruce, 6 equals 3.75. In a sentence, after 6 days, the puddle is 3 3/4 inches deep. See? When is the water depth 5.75 inches? Write your answer in D of T notation. I'm scanning, and what am I seeing? After 2 days, the puddle is a depth of 5.75 inches. So I would say D of 2 equals 5.75. So after 2 days. .75 inches. What questions do you guys have about your table? It's pretty sweet. All right, let's go ahead and take a look then at a graph. Pretend that we had Maria going on her trip. And Maria's trip started at home. She drove for a while and went to a museum. After visiting the museum, she drove some more and stopped for dinner. And then she returned home. Which variable is a function of the other variable? In other words, what depends on what? Is Maria's time into her trip depend on her distance from home? Or is Maria's distance from home depending upon what time in her trip we're looking at? What? That's confusing. I try to make a sentence in my head. What depends on what? Does her distance from home D depend on the time T in hours? Or does the time T in hours depend on her distance T from home? Which makes the most sense in this problem? What do you think depends on what? Nathan?
The time depends on the distance.
The time here depends on how far away she is from home.
Well, you know, distance depends on the time.
The distance she's away from home depends on the time in hours. I don't know. Cameron?
I was gonna say the same thing, distance depends on time.
Ethan?
That X and Y would apply.
Yes, 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 yes. You guys are all right. So typically our vertical axis variable depends on our independent variable, our horizontal axis variable. If we're looking at a graph, y is a function of x. This quantity typically depends on that quantity. Okay. Now, not always, but in general, we could safe to say the dependent variable is on the vertical axis, and the independent variable is on the x-axis. This makes sense contextually as well, because Nathan told us the distance Maria is from home depends on what time we're talking about during the day. Right? If we're talking about the morning, then she might be driving or at the museum. If we're talking about the afternoon or evening, she might be having dinner or coming home. So it depends, right? It depends on what time of day we're talking. So I would say that D depends on T, so I would say D of T. My domain is the collection of all T values such that 0 is less than or equal to T is less than or equal to 7. The range in blue is the collection of all distance D values such that D is less than, or 0 is less than or equal to D is less than or equal to, looks like my greatest distance away from home is what? What's the furthest Maria gets away from home? 100. Estimate Maria's distance from home after 3.5 hours. Go to the graph. When T equals 3.5 hours, how far away from home is Maria? I would guess about 83 miles. What? So I went to 3.5 hours and I jumped on the graph and I said, what distance is 3.5 hours paired with? So I went to my y-axis and I said that looks about halfway between 75 and 100, and if I could draw a straight horizontal line, I'd be close to 82.5, which I then rounded up to 83 and wrote as an if in function notation. So I'm just estimating. We don't have a function equation, right? We don't have a function equation, so I'm just looking, estimating. Estimate how much time it took Maria to be 100 miles from home. She was first 100 miles from home after what? 4? What's the significance of the left horizontal line segment? Estimate its endpoints. What's she doing at the left line segment? Right? Which part of the story? Which part of the story matches the left horizontal line segment? Nathan Z.
When she visited the museum.
I'm down. So she's probably at the museum then. Oh boy. Taking in some horizontal, I'm sorry, some historical artifacts. What was Maria's speed in miles per hour when she left home until she made her first stop? So that looks like this segment. Left home until her first stop at the museum. Keep in mind we can get miles per hour by doing change in distance in miles. I'll do D over change in time in hours. That would be miles per hour. D miles over T hours. So it looks like she went a change of 75 miles in a time of 1.5 hours. Calculator brain. Is that 50? Down? 50 miles per hour. Love it. Robert Wadlow is the tallest medically substantiated human being recorded in history. His father is 5 foot 11 and a half inches, so it's basically 6 foot. His father's not on the right, his father's on the left. Robert Wadlow only lived to be age 22, and at his time of death was measured to be 8 feet 11.1 inches tall. Yes, that's a real picture, no Photoshop. Interestingly enough, he died from an ankle injury at the age of 22. Can you believe it? Yeah. Well, think about all the stress that you would place on those joints, right, if you were that tall and that big. Okay, let's go ahead and take a look at this tabular information and answer some questions, and we have to get the vertical line test, so we've got to hurry. What's the domain of the function in our table? Guys, if it's a table, that's a list of discrete values, so we don't use set builder. If it's a table, we just list it. Everybody, let's go. So domain would be only 8, 10, 16, 18, 22. That's it. Because I'm looking at a table, the range is only the values shown in the table: 1.9, 2.0, 2.4, 2.5, 2.7. Find f of 16. F of 16 is 2.4. Bless you. What does it represent? His height in meters at age 16. So 2.4 meters tall at age 16. For what value of A does f of A equals 2.7? That's this point. A equals 22 years old. What's the reasonable practical domain? In real life, would his domain, his age, only be the years 8, 10, 16, 18? No, his practical domain would start at age 0 and go up until his time of death, age 22. So the practical domain will be listed in set builder notation because there's an infinite number of ages A, right, in his life, starting at 0 up until his time of death is 22 years old. Practical range then, our practical range would be H values. However, our H values, I would argue, wouldn't start at 0. What would our H values start at? Well, when he's born at time t equals 0, probably portion of a meter, right? No, that's at age 8. Oh. So right when he's born, I would guess like maybe 0.2 meters, right? Baby, a little bitty baby. So I'm guessing maybe 0.3 meters, 0.2 meters. Don't put M there. Sorry, don't put M. Whoa. Did you see that? That was awesome. All right. The last thing we're going to look at is how to tell graphically whether or not a given relation is or isn't a function. And think back to our definition of function. Each input that appears can only be paired with one unique output. If there's an input that appears more than one time, right, and paired with a different output, then it's no longer a function. So think of the definition of a relation and what makes a relation a function. What we're going to do is we're going to do the horizontal line test. We're going to take this line and we're going to drag it across my picture. This shows that if a given x value is paired with more than one y value, it's not a function. And so this particular graph, each x value occurs once. It's paired with unique output. So this first one is yes, it's a function. This is yes, this is a function. Versus the second picture, as I pull my vertical line across, I'm fine over here, but once I get in this range, notice how the same x coordinate, in this case -2, is paired with two different outputs. -2 is paired with -5 and paired with +5. So this is not a function because the same x input is paired with more than one y coordinate, more than one output. So this would be a no. No problem. This is a yes. It passes the vertical line test. So that's a yes. Bottom left. Does it pass the vertical line test?
Yeah.
Is it a function? Yes. Middle, does it pass the vertical line test? No. Is it a function? No. What is that? A triangle? Does this pass the vertical line test? No, it crosses the function more than, the relation more than one time, so that's a no also. That's a no too, Daphne. You guys are awesome and almost there. So all graphs are relations. Every single one of those graphs were relations. The vertical line test determines if a graph is a function or not. So the vertical line test states that if a vertical line intersects a graph at most one time, then the graph is a function. Stated the other way, if the vertical line crosses the graph more than once, then the graph is not a function. So our yes is there where yes, the relation is a function. Our no is there where no, the relation is not a function. Those were our yeses. Make sure you have those right. Yes, no, yes, no, no. Let's finish it out with our closure today. Ladies and gentlemen, think, don't call out. What's the domain of a function referred to? What's the range of a function referred to? And then true or false. All functions are relations. That's a true or a false. Number 4, all relations are functions. That's a true or a false. Number 5, so what is it that makes a function different than a relation? And that'll close out our discussion for the day. I'll be looking around the room for your written responses. You can check with your partner, but make sure that you keep your conversation quiet between the two of you, and then we'll share it with the whole class. Gotcha. 3.
Can we start packing up?
No. Okay, ladies and gentlemen, please don't pack up. We need to share responses. Thank you. What's the domain of a function referred to? So in general, what is the domain of a function referred to? Courtney? Pardon? Yeah, the collection of all inputs. So all of the inputs together is the domain. So the collection of inputs or independent variable values is the domain of a function. Good, thank you. The collection then of all outputs, right? The collection of all outputs would be the range of a given function. All functions are relations. Jen?
That's true.
That is true. To be a function, it has to be a relation, right? Already. All relations are functions. All relations are functions. What do you have for that, Cameron? False. And so no, that's not true. In fact, we just saw 3 relations in the last slide, those pictures that were not functions. Good job. So what is it that makes a function different than a relation? So what is it that makes a function different than a relation? All right, what's the defining feature there? Dong?
May only match up with one range.
Good. So each input matches with only one. Great work today, ladies and gentlemen. Now you may go ahead and back up, but please remain at your desk. Don't get up. Make sure if you borrowed a calculator that you do get up and return that to the tub to cross that out. Cross off the name and number. Great work today.